Hi, I'm Gene Chen, Yokogawa Stardom Product Manager. In this session, I'm going to review the API MPM 11.1.6.3 algorithm. This is in the Stardom Liquid library that's based on the API MPM liquid oil correction factors found in chapters 11.1 of the standard. The API MPM 11.1.6.3 is a method to correct volume and density from observed conditions to alternate conditions. And we've placed this into a function block that's now in the Stardom Liquid library. You may recall that 11.1.6.3, 6.2, and 6.1, those three algorithms are all based on customary base conditions, which is 60 degrees Fahrenheit at 1 atmosphere. So just as I've done with the other examples, I dealt one Excel spreadsheet that acts as an OPC client to Stardom's OPC server. The OPC server then communicates with Stardom's controller, and then we were able to view the data as it changes both in the control environment as well as on the Excel spreadsheet. So what I'm going to do now is go ahead and pull up the Logic Designer environment, and I'm going to go ahead and bring up the API MPM test sheet that I've created. And then we can view these side by side online with Excel spreadsheet. So now this is, I guess I can blow this up so you can read the whole thing. This is API 11.1.6.3. It covers method to correct volume and density from observed conditions to alternate conditions. And just as before, we have here on the left-hand side, this is the test case results area. It has both the inputs and the outputs. And then on the right-hand side of this slightly thicker bar, these are all the pre-configured test cases. So all you have to do is click on the example button at the top of each case, and then the inputs are transferred to the controller and then read back from the controller and displayed here in the results panel. Published standard, those values are right next to the calculated ones from the controllers for easy comparison. So let's go ahead and get started. We'll first select example 1. Before I do that, actually, I'll go ahead and bring up the Logic Designer engineering environment. So here I've got the function block shown in the Logic Designer environment, and you can see the inputs and the outputs as they change. So I select 1. These values are then loaded to the controller. In fact, it didn't look like it moved, but that's because what I've actually pre-configured here is the 11.1.6.2 algorithm. I need to scroll over here, and here's the 11.1.6.3 algorithm. Alright, so here are the inputs, and you can see that the inputs now indeed match. I've got the 823.7 observed density, which is shown here. Use a commodity group of 1, which is shown here, and the pressure and the observed pressure is -5, which is shown down here, and the observed volume is 1,000, shown here. So we've got all the key parameters here, which are the white background parameters. Those are all the inputs into the controller, and then we want to go ahead and compare the outputs. So all these outputs that are shown here, this is a subset of all the outputs that the function block actually generates. But we only are going to compare the specific variables that are published in the API standard, which is the density corrected to 60 degrees, the alpha 60 value, the CTL 60 GA. 60 GA means that's the temperature correction, volume temperature correction factor to go from an alternate conditions to base 60 degrees Fahrenheit. And then we also have the scaled compressibility factor. We have the volume correction factor for pressure to go from an alternate to 60 degrees base conditions. And then we have the combined CTPL. CTPL raw is used to correct densities, and CTPL is used to correct volumes. And so CTPL raw, this naming convention, 60GA, that's always in terms of volume from the standpoint of volume, so that would be used to correct from alternate conditions to 60 degrees base. But if you're correcting density, then you divide by this correction factor, because density is kilograms per volume, or mass per volume rather, so it's the inverse relationship, and that's why you divide. So you divide a density by the raw value to correct density, and you multiply volumes by the rounded value to correct the volume. And API standard, you round the value to 5 decimal places for the rounded value of the CTPL. And that's why it shows a little shorter here. Okay, so if we look at these, you can see that they identically match. And I'll just kind of give you a few seconds to look at them. And I'll go on to the next example. And we'll go to the example 2. You can see values changed here. If you stare at the logic designer side of the screen, when I do the example, you'll see these numbers flicker or change. And then you can immediately come over here. And as I said, another example is probably the easiest thing to do if you're doing a bunch of these in a row, is to go ahead and look at some of the key outputs. So the key outputs then are going to be volume, or do the volumes match, and do the densities match. So we can look at, does the density at corrected to 60 degrees match? Yes, it does. Does the density for alternate conditions match? Yes, it does. And then same thing, do the volumes at 60 degrees base conditions and alternate conditions, do they match? And they do. So we can kind of just keep going through these examples one at a time. I'll select the button to make the change, and we can see that they, again, the densities match and the volumes match. And if you want to, you can freeze this video and you can compare the other values. They will match as well. And again, just as in the other algorithms, we have a very high degree of precision. We match up to 8 decimal places or better in every case, and in many cases we match more, up to 10 to 12 decimal places. Like this one matches up to 12 decimal places. You can see that looks like a slight mismatch here. It's probably due to a rounding, but it's out at like the 12th decimal place or 9th or 10th. Let's count it. This alternate density, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. On the 12th decimal place, it all matches up until the 12th decimal place. Then I get a 5, whereas the standard, published standard yields a 4. It's still matched to 11 decimal places. 8's all you need for compliance. And I just think that's pretty cool that we're able to have such a high degree of precision. So let's go ahead and go to the next example. And look and see how that calculates out. Right. And once again, we have a high degree of precision. And as I said here, you can see the difference on the same thing, the alternate density. We have the last 3 digits being 580, and on the standard it's, sorry, I shouldn't say 580. The last digits that match the standard here, we have to count out. They only go to 6, 9, 12. So if I go 6, 9, 12, it ends on the 415. Then in the published standard, it ends on 416. But you can see, because I've expanded the cell here to show more degrees of precision in the Excel sheet, the actual number was 4158. So if you round that to the 12th decimal place, it becomes 416, which is what's published by the standard. So we match identically here. Just thought that's pretty cool. All right, we'll look at the 7th example. You can see that the decimal places match up, densities match up again, and the volumes match up again. And I'll just keep doing this on all these examples, giving you some time to quickly review that they match up, view that the controller side here does indeed has changed. I guess I can scroll down and compare the rest of them. And I'm only going to go through the examples up until they have an error. Once there's error conditions that we're supposed to test against, and maybe that's not quite as interesting for you to review. So I'll just keep going through these until we hit the error test cases. Okay, so that's changed. You can see that again, once again, we identically match. Okay, then we've hit the error test cases. There might be, I think if I recall right, yeah, at the end there's another one, a valid one that we can try. So this is test 12. And you can see, once again, we identically match on the results to a very high degree of precision. Okay, that concludes this video.